to a lot of small individuals. They go out of the core facility. So there's a lot of potential, and everybody already talked about this. Then now the sequencing is no longer the limitation. The challenge is actually now is how to analyzing all this big data. A lot of people already talk about it. We can develop some smart algorithms. What I want to talk a little bit about today is another angle to look at a problem. The way that how smart your algorithm is, fundamentally you still need those computational power. Traditionally, we use a lot of HPC, this including supercomputers and clusters. Although the cluster technology has been advanced so much in the past 2 or 3 decades, the cost of acquire and maintain a cluster or supercomputer is still beyond the reach of a lot of small research groups. So for the small guys, in order to fully leverage the power of next generation sequencing, I think we need some commodity HPC technology that's easily accessible to the ordinary people. So actually, GPU has been mentioned in one of today's earlier talk by Yang Xin. So basically, the graphic processing unit is just a video card in your computer. It has been existed for a while and has been used a lot by gaming, high-performance graphic processing. So thanks to those frantic gamers and the gaming industry, they keep pushing the limit of the demands of the high-performance graphic. So this video card has been made more and more powerful. And then now recently people figured a way to use it for general purpose computing. So how powerful is the GPU? This graph shows the growing power of the graphic processing unit compared to the CPU. As we can see, the latest NVIDIA GPU actually is 10 times more powerful than the most advanced Intel multi-core CPU. So just to give you a little idea, this GPU has 512 cores. And then just put it into the perspective, it can perform 10 to the power of 12 floating point operations in 1 second. This number, the performance, if you put into the 2004, it can make to the top 500 supercomputer, the fastest supercomputer in the world. So that's why people call this personalized supercomputer. So you may say that if the GPU is such powerful, so why not everybody just use it? Then to answer this question, let's take a quick look back to the history of the CPU design. I know a lot of you here is not from computer science and try to make things simple. Well, simple CPU core, basically you need 3 components. The control theory of control component, how do you fetch the instruction, basically the task, tell the compute component how to do it. And then the arithmetic and the logic unit, which do the actual computation. You also need some register to save the execution context. That's it. In the past 2 or 3 decades, the computer industry have been focusing on increasing the frequency of the CPU. So basically, the idea is simple. We just keep increasing the frequency of the compute component. Hopefully, can perform process more and more tasks in the same amount of the time. This has been successful, and the people found actually when they're scaling up the frequency of the computer component, which is the arithmetic and logic unit, they found that the challenge is actually how to supply sufficient instruction and data to keep this unit busy. This is a part of the reason because it's relatively easy to scale up the frequency of the CPU, but it's very difficult to increase the speed of the memory. Regardless, to address those challenges, so the vendors have been doing a lot of innovation to trying to put more and more complicated logic and component to keep up with the frequency scaling of the compute component. This has been successful in from 1986 to early 2000, where we see every 18 months the CPU the frequency just doubled. And after early 2005, Intel started to figure out a problem with such approach, because when you do this, you have to pack more and more transistors in a small chip area. Then it will increase the power density. The problems become, it is getting harder and harder. This is the graph from Intel in the early 2000s. Just do a simple extrapolation. If we keep doing what we have been doing to increase the CPU performance, the temperature of the CPU will actually be getting close to the sun's surface. So the problem is we just simply cannot cool such a thing. So notice there's a problem. The GPU take a radically different approach to design the processor. The one idea is that, okay, let's go back to using a very simple dump core. Instead of increasing the performance of a single core, they use a vectorization to replicate this compute component. So the idea is that instead of optimize the performance of a single thread or single core, we use a lot of parallelism, use a lot of a processing unit to improve the throughput, the kind of throughput-oriented computing. So what we're seeing this is now let's get back to the earlier question. If GPU is such a powerful device, why don't we just use it? So the reason is that there's one caveat. The GPU architecture is radically different than CPU. Therefore, although we see it as a peak power, it's much better than CPU. In order to realize such a performance, it's difficult. So one thing is that because GPU cores are very weak or less powerful compared to CPU core, if you just use the CPU program running on this, you will fail miserably. So a lot of things we need to do or we can do to optimize performance. For those of people who are not from computer science, you just think about this. Instead of you having giving you a fast running port, you are giving an army of snares. And these snares are synchronized. They can only take the very simple instruction, and they will do everything together. So if you want to tell a different snare doing different things, it will be very inefficient. So that's the challenge of how to leverage the power from the GPU. All right, regardless, we still think that the GPU has a lot of power or potential. So we start exploring some of the efforts on how to accelerate the sequence alignment on the GPU, because the GPU is because the sequence alignment is very important, especially during my personal conversation with some of you during the coffee break. Some of you already observed, even nowadays, the sequence alignment in your pipeline can take days or even weeks. So we have been doing, we have completed 3 sequence alignment on GPU, one RNet. This is the short remapping algorithm. Probably it's not as well known as the BWA. It is the hash table based, space seeding based, the short remapping algorithm. And it has a Smith-Waterman as classical dynamic based, program based the sequence alignment. It can produce the optimal sequence alignment, but it's very slow. So there's a BLAST-P, the golden standard of the sequence database search. And we're also in the process of accelerating the indirect realignment. So the initial result is actually pretty promising. We see we have 10-fold speed up of RMAP. We have 30x speed up of the Smith-Waterman for the small sequence. And then for BLAST-P, we can speed it up for 6.5. So the 6.5 fold maybe not that exciting, but if you think about it, the GPU is just there, it's in your computer. You don't have to acquire any additional hardware. Even my laptop has 16 cores, but the GPU on my laptop has 16 cores. It will run it and get some speed up. It will be very nice. But we also find out during accelerating the velocity, we believe there's some way to further accelerate the performance in the process of doing that. So I want to share some of the lessons we learned. Again, it's a very, very high level. So one thing we found is that some algorithm, if the CPU optimized, actually it's very difficult to optimize on the GPU. Just think about it, because of the architecture is largely different. For example, for the velocity algorithm, it's much, much faster than Smith-Waterman on the CPU because they use a lot of heuristics like a seed and extension. However, by doing so, you introduce a lot of divergent branching, which will be really, really bad on the GPU. So that's why the speed up is only 6.5x. Another lesson we learned is that we really need to rethink the algorithm design in order to fully leverage the power of the GPU. I'll give you an example for the RMAP. Originally, they used the hash table to do the K-more matching. This is a standard algorithm on the CPU. It's very, very efficient. However, we found on the GPU, because the hash table can incur some collision. So again, the collision and then increases, in turn, have the divergent branching is bad on GPU. And then what we did, we actually scaled back and we used a dumper algorithm. It's a binary search. If you know a little bit of programming, the binary search actually is less efficient than the hash table on the CPU, but it's more scalable. So on GPU sometimes, just think about, again, the army of snails. So you got to have, if your program is scalable to efficiently utilize all this snail, it actually is better than the program that is optimized for the CPU, but it will increase some imbalance in the device. So we believe there are some opportunities on the using sequence alignment to do accelerating sequence alignment on GPU. There's what we will find is there's two different steps we can do. The first thing we can do, we know there is some algorithm as the fast but less accurate, like blast and bow tie mapping. There are also some algorithm that is slow but very accurate, like one of the speakers mentioned minimum wounds. They're basically the same as the Smith-Waterman algorithm. And then we have the BWA sequence alignment. So first thing we can do, because of this algorithm, typically they are more regular than some fast algorithm like a blast P. So first thing we can do, we can speed up this. So if we bring it up in the level that the execution is comparable to the fast algorithm, that is a win. So it's also possible for the next new algorithm, but if we want to do something fast and both faster and more accurate, then we probably need to write the programs from scratch. That's why the computer science guy would need a lot of help from the biology community. Let me quickly almost close it with something called a computer queue initiative. So NVIDIA also figured out some of the NVIDIA basically they have a goal. They want to leverage the GPU power to help the cancer cure research. And they talked to a lot of people that believe the sequence alignment is the first step. And then we're partnering with them. Everything is in very initial and preliminary stage. We don't know where it's heading to, but the goal is to develop a framework that allow people easy to develop sequence alignment and optimize sequence alignment on this framework and easily plug it in whatever workflow you have. And this is, I believe, that this software can bridge to the metagenomics community. All right, I'm done. The conclusion is the market type DNA sequencing. You need also need very accessible HPC resources, and GPU has the potential, has a lot of work to do. We'd like to thank the NVIDIA for the sponsorship of the program. Okay, thank you.
Thank you very much. since we're way behind, I'm going to move on to the next speaker.